So today we will discuss about a topic called transformer. So in the previous classes we already read about the DC generator motor. So next we'll move to the next topic, which is called as transformer. So these are the contents on which we'll have a discussion: introduction, construction, principle of operation, and EMF equation. So at first the introduction. So still now we have read about generator, motor. As we know, generator is used to convert the mechanical energy to electrical energy. Motor is used to convert the electrical energy to mechanical energy. Next, what is a transformer actually doing? So the first point says transformer is a static or stationary electrical device. So first we are going to terms called, one is called as static or stationary. So before going to discuss all these points in detail, first we will read that why the transformer is called as a static device. Okay, and we'll also read that why this is called as a stationary device. So as the definition says, it's a static electrical device. Okay, so we know that we have read about generator, we have read about motor. In generator and motor, both are works upon the principle of Faraday's laws of electromagnetic induction. And whenever this generator and motor working, the two things are mostly required. One is called the magnetic field, and the second thing is that the conductor. That means for operation of the electrical machine, either that is a generator or motor, two things are required. One is called as magnetic field, other one is called as conductor. And we know that depending upon these two, the Faraday law says either the magnetic field can be changed or the conductor can be changed. If the magnetic field changes, EMF will be induced. If conductor changes, then also EMF will be induced. Depending upon these two things, either magnetic field changes or conductor changes, we can divide the induced EMF. We can divide the induced EMF into two types. One is called as statically, other one is called as dynamically. Okay, in case of DC machines, whatever the DC machine we read, in that case what happened? The conductor placed between the magnetic field is there, between that conductor is present, and the conductor moves across the magnetic field so that the magnetic field will be cut or the magnetic flux will be cut, so that EMF will be induced in the conductor. That is called as dynamically induced EMF. In that case, in case of dynamically induced EMF, here the conductor changes its position. Okay, here, but the magnetic field constant, they are not changes. So where the induced EMF, where the conductor changes its position but the magnetic field constant, so due to the conductor changes position, magnetic field cuts, so that whatever the EMF will be induced, that is called as dynamically induced EMF. Next thing, when you are going for a statically induced EMF, just the opposite one. Here conductor changes, magnetic field constant, but in this case magnetic field will be changed, conductor will be constant. So in this case, here magnetic field or flux changes, but here conductor constant. Constant means it doesn't change its position, just the opposite one. In this case, the magnetic field or flux will be changed, conductor will be constant. So whenever we are reading about the transformer, it is called as a transformer, static electrical device. In this case, the magnetic field or the flux which is linked to the conductor changes, but the conductor will not change its position, it will be as it is. So as per Faraday law, if the magnetic field changes with respect to the conductor, then EMF will be induced, and that induced EMF is called as statically induced EMF. So the operation of a transformer or whatever the EMF induced in a transformer, that is called as statically induced EMF. Due to this one, this transformer is also called as a static electrical device. Another term is called as stationary. So whatever the generator we have read, DC machine, generator, motor, in that case some rotating part is there. We are having the magnetic field, magnetic poles, between that we are putting an armature conductor. So when the armature conductor will be rotated, so we can say there is some rotating part is present. But in case of a transformer, there is no such rotating part. Whatever the conductor we are taking, whatever the different parts are there, they are fixed, they are not changes, they are not rotating. So simply we can say in a transformer there is no rotating part. That's why it's also called as a stationary device. So the stationary in the sense of means no rotating part. Okay, no rotating part. So since there is no rotating part in a transformer, it's also called as a stationary electrical device. So these are the first 2 points, static or stationary. Next we'll go what a transformer is actually doing. Okay, so the first point says transformer is a static or stationary electrical device which transfers the electrical power from one circuit to another circuit. So in case of DC generator and motor, in generator the energy means the mechanical energy is converted into electrical energy. In case of motor, the electrical energy is converted into the mechanical energy. So there is some energy conversion is there. But when you are talking about the transformer, there is no such energy conversion. What you are doing, we are just transmitting or transferring the power from one circuit to another circuit. So the first point says it transfers electrical power from one circuit to another circuit. And during transmission, it can do this by increasing or decreasing the voltage, by decreasing or increasing the current. So whenever we are taking a transformer, by using a transformer, we can transmit the power from one circuit to another circuit. And when you are transmitting the power will be constant. Whatever the input power you are giving, the output power will also be same. Power will not be changed. But during transmission, we can increase the voltage or we can decrease the voltage. If you are increasing the voltage, at the same time current will be decreased. If you are decreasing the voltage, at the same time current will be increased. So the second point says it does this by increasing or decreasing the voltage, by decreasing or increasing the current. So whenever we are increasing the voltage, at the same time current should be decreased. If you are decreasing the voltage, current should be increased. Next one says does this without changing the frequency. So transformer is a AC electrical device. So when we are talking about AC, there must be frequency present. So whenever we are transmitting the power from one circuit to another circuit by changing the voltage, by increasing the voltage or decreasing the voltage, frequency must be same. Input frequency must be equal to the output frequency. So power must be same, frequency must be same, but voltage and current may be vary. Okay. Last point says that accomplishes this by electromagnetic induction. So these 3 points says that what is a transformer is actually doing, but how it can do. Last point says accomplishes this by electromagnetic induction. So we have read about Faraday's law. We have read about the Faraday's laws of electromagnetic induction. So depending upon this method, the transformer also works. Just like DC generator, DC motor we have read, depending upon Faraday's laws of electromagnetic induction, this machine is actually working. And again, when we are talking about the Faraday law, this includes self-induction and mutual induction. Okay, so we'll discuss one by one what is self-induction and what is mutual induction. We'll discuss one by one. So still now we read that transformer each transmitting the power from one circuit to another circuit. During this, voltage changes, current changes, frequency constant, power constant, and this works upon Faraday's laws of electromagnetic induction, which includes self-induction as well as mutual induction. Next point is that why transformer? Because we have read about generator, motor, that these are the devices which are used to convert the energy. Maybe sometimes electrical to mechanical or mechanical to electrical. So when we want to use some mechanical energy, then we will use a motor. Either that is a DC motor or AC motor. If he wants to use some energy, electrical energy, then in that case we can use a generator and he can generate the energy. But what is a transformer is doing? As in the first slide I told you that transformer is not a energy converting device, but it can only transfer the energy. So why we are using a transformer? So we have read about different types of power stations. As I told, once the energy will be generated, just by using law of conservation of energy, we can only convert one form of energy to another form of energy. And while converting this one, we can use one source of energy that can be converted into the electrical energy. And in case of power stations like hydro plant, nuclear plant or thermal plant, they are using some energy, like in case of hydro plant we are using the water energy, in case of thermal plant we are using the heat energy, in case of nuclear plant we are using the nuclear energy. So by using the different sources of energy we are generating the electrical energy. And once the energy will be generated at a particular place, at a particular power station, that should be transmitted over a long transmission line where it can be utilized. Utilized means it may be in a town, it may be some places where the energy is utilized. So the power station may not be situated to the same place where it will be utilized. Power station is somewhere and the utilization is somewhere place. So between the power station and the utilization place, there is much more distance is there. That means once the energy will be generated, the electrical energy will be generated, that will be transferred over a long distance where it can be utilized. And in India, whatever the power stations we are having, obviously we know that we have to use a generator to generate the electrical energy. Unless using a generator, we are not able to generate the electrical energy, because generator is only one device by using which we can generate the electrical energy. If in a power station we are using a generator, at maximum, in India, at maximum, whatever the electrical energy you are generating, that is in terms of 3.3 kV, 6.6 kV, 11 kV or 33 kV at maximum. This one is the maximum value. Wherever we are going for a power station, at maximum the voltage or the energy can be generated at a 33 kV, not beyond that. If you are going to generate the voltage beyond this value, then the generator size, whatever the generator size we are taking in a power plant, that size will also be increased very high. That will be increase the cost. So much of factors are there. If you are just taking a generator which will be generate more than 33 kV, then the size of the generator will be increased, then cost will be increased, maintenance will be increased. So many factors are there. So to avoid that cost, to avoid that, that means the generation cost, to avoid the maintenance cost, instead of going for a high rating of a generator, we are using one such device through which the voltage can be stepped up. So in case of, as I told you, that we are generating at one place, we are transmitting over a long distance where the energy can be utilized. But during transmission, there is some loss of energy. How much energy you are transmitting, during the transmission there will be some loss of energy. And the loss of energy means, we know we are taking the conductor lines, we are just using some conductor lines so that the current or the power can be transmitted. We might have seen the high voltage lines, the roadside, we might see the high voltage lines. Okay, so by using that transmission lines, we are transmitting the power at voltage. So during this transmission, one loss is called as copper loss, I square R. Okay, which is called as copper loss. We know that once we are taking a transmission line, every transmission line is a conductor that has some resistance. So we cannot make the resistance to zero. If you are taking a conductor, that conductor must some resistance. It cannot be made to zero. Only we can reduce it. So whatever the conductor we are taking, that conductor has some resistance. So if you are using that conductor to transmit the electrical power, we know, as the formula says, that I square into R, which is called as the copper losses. So when you are transmitting the power from one place to another place by using the transmission lines, across that transmission line there will be some power losses, which is called as the copper loss. If we are not able to reduce the resistance, we can reduce, but up to a certain limit, we cannot make to zero. So resistance must be there. But if you are not able to control the current, then these losses will be increased. So if you want to reduce the copper losses, you have to reduce the current. Obviously, once we have taken the conductor, the resistance is fixed. The resistance we are not going to change. But what we can do, we can change the current. If you reduce the current to such a value so that the total copper loss can be reduced. So our main concern is on the current. So we have to reduce the current so that copper loss can be reduced. We know Ohm's law. What is Ohm's law? Yes? What is Ohm's law? Okay, so Ohm's law says that at constant temperature, it's an important point, at constant temperature, the current is directly proportional to the potential difference. So as per Ohm's law, as per Ohm's law, at constant temperature, constant temperature, I is directly proportional to V. But if the temperature will not be constant, this relation holds good when temperature is constant. But if the temperature will not be constant, then I is inversely proportional to V. When temperature not constant. Okay? So when the temperature will not be constant, I is inversely proportional to V. So whenever we are transmitting the electrical power from one particular place to another place, we are taking throughout the day, throughout the month, throughout the year. And we know that if you are taking a particular day, let's take today. So today, what was the temperature at 6 o'clock? The same temperature will not be at 12 o'clock. That will be changed. If you again go at 4 o'clock, 4 in the afternoon, again temperature changes. So if you are taking it 24 hours a day, throughout the day temperature continuously changes. So in that case we can say temperature is not constant. If temperature will not be constant, then I is inversely proportional to V. That means if you want to reduce the copper loss, as I told you that you have to reduce the current. You have to reduce the current. If you want to reduce the current, what you have to do? You have to increase the voltage. That means if you want to reduce the copper losses, the voltage, the electrical power which is transmitted over the transmission lines, that voltage will be a very, very high voltage. If you increase the voltage to such a high level, current will be reduced. If current will be reduced, automatically copper losses will also be reduced. That means to reduce the transmission losses or to improve the efficiency of the transmission line, the voltage or the power should be transmitted over at a high voltage. But as I told you that in India at maximum we can generate up to 33 kV. We cannot go beyond that one. If you are going beyond that one, you have to go for a big size generator which will be cost more. So to avoid this kind of things, we are having one machine, one electrical machine which is called as transformer. So by using the transformer, the maximum voltage, either 11 kV, 33 kV or 6.6 kV, that can be stepped up to a very high voltage. High voltage in the sense of either that can be stepped up to 132 kV, okay, 220 kV or even up to 400 kV. Okay, so the same voltage, how much voltage we are generating, the same small amount of voltage, just by using a transformer, we can step up or we can increase the value of the voltage to such a high level. If you increase the voltage to such a high level, current will be reduced as per this relation. Current will be reduced, automatically the losses will also be reduced. If the losses will be reduced, then the efficiency of the transmission line will also be improved. So by using a transformer, simply we can say we can improve the efficiency by reducing the losses. And how that can be done? By improving or by increasing the voltage to such a high level. Voltage increase, current reduced, copper losses reduced, efficiency increased. So due to that one, to reduce the losses, to increase the efficiency, we are using a transformer. Okay, so this is the reason why we are using a transformer. Next one is that construction. What are the different parts are present in a transformer? So these are the two basic things in a transformer. The two most basic things are, one is called as the windings. Okay, one is called as windings, that is called as two windings are present. One is called as primary winding, secondary winding, and the next one is that a common laminated magnetic core. Okay, so in that case what happened in case of a transformer, let me just show the figure so that you can easily identify here. So in case of a transformer, two most important things are, two windings are present and one common laminated magnetic core. Two windings in the name of, one is called as a primary winding and second one is called as secondary winding. So this is as per construction. Okay, so in every transformer there are two windings are present, primary winding, secondary winding, and both these windings are wounded on a common laminated magnetic core. So this was your core. You are seeing this one is called as your core, and these are, this one is called as winding, this one is called as another winding. And depending upon the way the windings are connected, we can call one winding as a primary winding, the another winding as a secondary winding. So still now we have read that we are using a transformer. and it is used to transfer the power from one circuit to another circuit. So to transfer the power, the transformer should be connected in the circuit. So one side source will be connected, one side load will be connected. So the winding which is connected to the source, that is called as primary winding, and the winding which will be connected to the load, that is called as a secondary winding. So if somebody will give you a transformer and it will be asked to identify that which one is a primary winding, which one is secondary winding, it's not easy to identify, because the way you will connect, depending upon the name, that will be given. So if it is a transformer is there, if I connect the primary winding to the supply side, that will be called as a primary winding. If the other one will be connected to the load, that will be called as secondary winding. I can also interchange. If I am taking this one, this is the core I have taken, and this is the primary winding. So if I will connect this one, to the source means the supply. If I will connect this one to the source, then this will be called as primary winding. And if I will connect this winding to the load, then this will be called as your secondary winding. So it totally depends upon us, the namings of the winding, depending upon how they are connected. If I make it interchange, if I will connect to the load, then again name will be changed. If I will connect to the source, then again the name will be changed. So the namings of the windings mostly depends upon how they are connected. Either that is connected to the source or that is connected to the load. Depending upon that one, the namings will be given. And both the windings are wound on a common laminated magnetic core. So this one is called your transformer core. And here one winding is present, here one winding is present. And both the windings are wounded on the core. This one is called as a laminated core. So we will read about later the losses. When you will read about the losses, there I told you why you are taking a laminated core. Okay, so this as per the construction, primary winding, secondary winding, and a common laminated magnetic core. Except this also, these are, as I told, these are the basic parts. Windings and core, these are the basic parts. Except this one also, the transformer has some other parts that will be discussed later. Okay. Next, the transformer classification. What are the different types of transformers are there? So depending upon the first point, depending upon the transformer phases. So in earlier classes we read about that AC circuit. The AC circuit can be a single phase circuit, can be a three phase circuit. Okay. So depending upon the transformer, either the transformer is used for a single phase circuit or for a three phase circuit, the transformer can also be divided. Depending upon the construction. If the transformer is constructed which can be used in case of a single phase circuit, that is called as a single phase transformer. If the transformer is constructed in such a way that can be used for a three phase circuit, that will be called as three phase transformer. So there are some other constructions there, that means some star connection, delta connection is there, that you did in three phase circuit. The same theory is also applicable for the transformer construction. Some star connection is there, delta connection is there. So depending upon that one also, we can say that either the transformer is a single phase transformer or a three phase transformer. Okay. Next one is depending on the voltage at which the winding is operated. So as I told you that we are having two windings, primary winding, secondary winding. And the winding which will be connected to the source, that will be called as a primary. Winding will be connected to the load, that is called as a secondary winding. And as I told you that in case of a operation, the transformer is used to transmit the power from one circuit to another circuit. And while transmitting, it can increase the voltage or decrease the voltage. So depending upon the transformer, either the transformer is increasing the voltage or decreasing the voltage. The first point is that depending upon the voltage level, that means either it increases the voltage or decreases the voltage. Depending upon that one, the transformer can be called as a step-up transformer, it can be called as a step-down transformer. So in step-up transformer, as it is written that the primary winding is low voltage winding. That means in case of a let me go through the diagrams. Here you can see, in the first one, it is a step-up transformer. So step-up means here the voltage will be stepped up. How much voltage we are giving to the primary winding, the same voltage will be increased in the secondary winding. So here you can say, here this is the primary winding which will be connected to the supply. This is the secondary winding which is connected to the load or to the output. So here we are giving this as the input, here we are getting as a output. So if you are giving the voltage, some value of the voltage, if the transformer is able to increase the voltage, then that will be called as a step-up transformer. Similarly, in this case, step down transformer, in this case, whatever the voltage we are giving, that voltage will be step down. So now you can see the check the values also. Here, let's say we are giving a 1000 voltage with a current rating of 2 ampere. At the output, the voltage will be decreased because we are talking about a step down. So the voltage, how much voltage we are giving, that voltage will be stepped down. 1000 voltage, we are getting here 200 voltage. And we know that whenever the voltage will be increased, at the same time current will be decreased. If voltage will be decreased, current will be increased. Just opposite. See here, voltage is 1000 volt, current was 2 ampere. Here, voltage will be 200 volt. Now the voltage is reduced and current is 10 ampere. And also we can see but in case of a step up, just the opposite thing. Whatever the voltage we are giving here, the voltage will be increased. If the voltage will be increased, current will be reduced. That means here, whatever the voltage we are giving, whatever the current will be present in the supply side, that current will be reduced here and voltage will be increased. And one more thing is also, see, we can see that one. Here, these are the coils are present. We can see how many turns are present. If you are going for a step up transformer, if you compare the number of turns present in the primary winding with that number of turns present in the secondary winding, here number of turns will be less than the number of turns in the secondary winding. Similarly here, if you check the number of turns here more than the number of turns in the secondary winding. That means in a single sentence, if you are going for a step up transformer, okay, here in this case voltage is increased. That means V1, if this is the primary voltage, in this case V1 is less than V2 because this is the primary voltage, V2 is the secondary voltage. So primary voltage is less than the secondary voltage, or simply you can say here voltage is stepped up. If V1 is less than V2, then here you can say I1 is greater than I2. Okay, and one more thing is that number of turns, N1 is less than number of turns in the secondary winding. N1 is called as the number of turns in the primary winding, N2 is called as the number of turns in the secondary winding. So these are the some values related to the step up transformer. V1 less than V2, I1 greater than I2, N1 less than N2. And when we are talking about a step down transformer, just the opposite things. So in this case, voltage is stepped down, means voltage is decreased. So in this case, V1, the source voltage, is greater than the load voltage. If V1 is greater than V2, then current I1 is less than I2, because while increasing the current or while increasing the voltage, current is reduced. Similarly, the same thing, N1, number of turns is greater than number of turns in the secondary winding. So here, number of turns in the primary winding is more than the number of turns in the secondary winding. Okay, so this is depending upon the working operation. That means either the transformer is increasing the voltage or decreasing the voltage, depending upon that one, step up transformer and step down transformer. The next thing is that depending upon construction. That means as I told you that two things are there, winding is present, core is present. So depending upon the position of the winding and position of the core, the transformer can also be divided into two types. One is called as cell type, one is called as core type. Just go through the diagram, you can easily identify. So this is called as core type. So here, this one is called as winding, this one is called as core. So in case of core type transformer, winding surrounds the core. That means if this is your winding is core is present, on that core some windings will be present. So we can say in case of a core type transformer, winding surrounds some part of the core. That means winding covers some part of the core. That is called as core type transformer. In case of cell type, just the opposite. Here, this is your core, the outer side, winding is present inside. That means in case of a cell type transformer, the core surrounds the winding. That just the opposite. Here, winding surrounds the core. That means winding will cover some part of the core. In this case, in case of a cell type transformer, the core surrounds the winding. That means core will be, winding will be present here, and the outside core will be present. So just the opposite case. So just by looking at the diagram, we can easily identify which one is a core type transformer, which one is a cell type transformer. So these are the some of the points depending upon which we are dividing the transformer: step up transformer, step down transformer, single phase, three phase, and core type, cell type. Next, So still now we read what are the different type of transformer, what a transformer is actually doing. Next, the important thing is that the principle of operation, how the transformer is working. That means how we are giving a supply voltage so that the same supply voltage is increase, decrease in that load side or in the source, the output side. So here the principle of operation of transformer is based upon Faraday's laws of electromagnetic induction, which includes self-induction and mutual induction. So now the question is, what is Faraday's law? Anyone? Okay, so Faraday laws, the Faraday law of electromagnetic induction has two statements. In first statement or in the first law, it says that how the EMF is induced. Second statement says what is the magnitude of the induced EMF. So in the first statement says that whenever there is a change in flux, EMF will be induced. Same thing can also be taken in another way. Whenever the conductor will cut the flux, EMF will be induced. So the result is same. Result is induced EMF. But how the EMF will be induced, that depends upon the two different things. Either conductor changes or flux changes. So that I have already told you. So depending upon the Faraday law of electromagnetic induction, the transformer is actually working, and which includes self-induction as well as mutual induction. So just go through a diagram, they can easily identify. Now this one. So we have taken a transformer core is, this is the winding which is connected to the supply. So this is called as primary winding. This is the winding which is connected to the load. We have taken a resistive load, so this is called as a secondary winding. So transformer core, primary winding, secondary winding. So what we are doing here, we are supplying the voltage to the primary winding of the transformer. As we know, this is a AC device, so we have to supply the AC. If you supply DC, transformer will not work. I will tell you later why that if you are supplying a DC, why the transformer is not work. So here we are supplying AC voltage. So when you are giving AC voltage to the primary winding, due to the supply voltage, since this is a closed one, whatever the coils we have taken, here the coils are having some number of turns on the core, and one terminal is connected to here, one terminal is connected to here. So now this is a completely closed one. So whenever we are giving a supply voltage, then a current will be starts to flow through the primary winding. Okay, and since supply voltage is an alternating one, current will also be alternating one. So due to the supply voltage, which is a alternating voltage, an alternating current will be starts to flow through the primary winding. And when the alternating current will be starts to flow, we know that whenever a current will be starts to flow through a conductor, some flux will be generated. Yes. So whenever alternating current will be starts to flow through the core, then due to the alternating current, some alternating flux will be starts to flow through the windings. Some alternating current will be starts to flow through the winding. And since the winding is wounded on the common laminated magnetic core, whatever the flux will be produced across these coils, the same flux will also be linked to the core. Okay, here we are supplying alternating voltage, alternating current starts to flow. Due to the alternating current, some alternating flux will be produced, which will be linked to the whole core. And we know that as per Faraday law, if the flux changes, EMF will be induced. So whatever the flux is linked to the core, whatever the flux is linked to the primary winding is alternating one. Alternating flux means what? If you plot a waveform, we will get a waveform like this. This is called as time, and this is called as your flux. That means if you take each interval, t is equal to 0, t is equal to 1, t is equal to 2, and so on, at each interval the flux is changes. Here it has some value, here it has some value, here it has some value. So the flux is continuously changes. So if the flux will be changed, as the Faraday law says, if the flux will be changed, EMF will be induced. That means alternating current flowing, alternating flux is there, and since the core is constant, core is not moving. So if the flux will be changes, or if the flux will be alternating one, then across the primary winding some EMF will be induced. So for example, we have taken the voltage, supply voltage is Vp, current flowing through the primary coil is Ip, and we have taken the number of turns in the primary winding as Np, number of turns Np. So depending upon the supply voltage, depending upon the current flowing through the coil, depending upon the number of turns present, and depending upon the flux produced, some EMF will be induced in the coil, which is called as the self-induced EMF. In the previous slide I show you that in case of a transformer, it basically works on Faraday law of electromagnetic induction, which includes self-induction as well as mutual induction. Self-induction means here what happened, we are supplying the voltage to the same primary winding, and due to the supply voltage, whatever the EMF will be induced in the primary winding, that EMF is called as the self-induced EMF. That means to which winding you are supplying the voltage, in the same winding EMF is induced. So due to the alternating flux, whatever the voltage will be induced in the primary winding, that EMF is called as the self-induced EMF. And that formula, is given by, okay, this is given by self-induced EMF, which is given by minus of NP into d phi 2 dt. Okay, minus of NP into d phi 2 dt. So d phi 2 dt means the change in flux, the time rate of change of flux. NP stands for the number of turns in the primary winding. So if you go to the Faraday's second statement, second law, that will say the magnitude. So depending upon the number of turns present in the core, depending upon the flux changes, rate of change of flux, that many amount of EMF will be induced. So let's take this one as EP, EMF induced in the primary winding, that is given by minus NP into d phi by dt. So I'll tell you later why we are taking a negative sign. Next thing, so here flux linked to the primary winding. Since this is a common laminated core, whatever the flux will be linked to the primary winding, same flux will also be linked to the secondary winding. Same flux, whatever the flux linked to the primary winding, same flux linked to the secondary winding. That means flux remain same. Same flux will be linked to the secondary winding. Again, the flux which was linked to the primary is alternating one. So whatever the flux linked to the secondary, that is also alternating one. So again in the second side of the transformer, again due to the alternating flux, EMF will be induced. Okay, which is called as mutually induced EMF. Mutual means here in this case, we are supplying the voltage to the primary winding. We are not supplying the voltage to the secondary winding. Whatever the voltage we are supplying, the VP is supplied to the primary winding. But due to the mutual induction process, some voltage will be induced in the secondary winding. So due to the mutual induction process, whatever the EMF induced in the secondary winding, that is called as mutually induced EMF. And the formula for that, which is called as mutually induced EMF. Okay, and take this one as ES, EMF induced in the secondary winding, that is given by minus NS into d phi 2 dt. Okay, d phi 2 dt stands for the rate of change of flux, NS stands for the number of turns in the secondary winding. So if you see these two equations, d phi by dt, this one is here same, only which one changes? NP and NS changes. So this is the way how a transformer is working. So we are supplying the voltage, EMF induced, again here also EMF induced. And if this, okay, once the EMF will be induced in the secondary winding, if the secondary winding will be a closed one, then the current will be starts to flow. So if you are not making this one as closed, even though EMF will be induced, current will not be starts to flow, because we know that unless and until current will not get a closed path, it will not flow. So if you are connecting a load to the secondary winding, due to the induced EMF, which is called as mutually induced EMF, current will be starts to flow through the load. Okay, so here we are, as I told you that d phi by dt both are same, only the change is NP to NS. So as in the previous that depending upon the types, we have read about step up transformer, step down transformer. So depending upon the NP and NS value, either that transformer can be called as a step up transformer or step down transformer, because there I told you that when we are talking about a step up transformer, here N1 is less than N2. In a step up transformer, number of turns in the primary winding is less than the number of turns in the secondary winding. So if in this case N1 means NP, here N1 means NP, N2 means NS. If NP will be less than NS, then that will be called as a step up transformer. If NP is a less value, then EP will also be less. That means we can say EP will be less than ES. That means we can say voltage in the primary winding is less than the voltage in the secondary winding. So that is called as a step up transformer. If for a step down transformer, here we know that N1 is greater than N2. Means we can say MP. MP is greater than NS. If MP will be greater than, then if you put a higher value of MP, then we can say that primary voltage is greater than secondary voltage, which is called as a step down transformer. So just by choosing the proper number of turns, the transformer can be taken as a step up transformer, can be taken as a step down transformer. So this is the way how a transformer is working. Next we'll go, that is the last one, EMF equation. So still now we have read that we are having different types of transformer, how a transformer is working. Then what is the EMF equation? That means if you are giving some voltage to the primary winding, the supply voltage, how much voltage will be induced in the primary winding, how much voltage will be induced in the secondary winding. So to find out that one, there is some EMF equation is there that you have to read. So to finding out that one, we are having different methods are there. Two methods are there to derive the equations. As the slide says, the EMF in the first winding, that is given by E1 is equal to 4.44 Fn15. One thing I forgot to tell you. So here we are getting the equation is how much? EP is equal to minus NP into d phi by dt. Here we are getting a negative sign. Okay, but voltage will not be negative. This negative sign indicates that we have no Lenz law. What is that? Lenz law. Okay, so as per Lenz's law, the EMF induced in a conductor or in a coil is always opposite to the cause due to which it is produced. So in this case, this EMF induced is only due to the supply voltage. Unless and until the supply voltage will not be there, EMF will not be induced. So this negative sign indicates that whatever the EMF induced in the primary winding or whatever the EMF induced in the secondary winding, that is always opposite to the supply voltage due to which it is produced. So this negative sign indicates that's the same. That is, as per Lenz's law, EMF induced in a conductor is always opposite to the cause due to which it is produced. And in case of a transformer, the supply voltage is the main cause for which EMF is produced. So this induced EMF always opposite to the supply voltage, and it will tries to make the supply voltage to 0. So to indicate that one, we are taking a negative sign. Okay, similarly in the secondary EMF also, we are just negative sign indicates that it is opposite to the supply voltage. Okay, so next we will go to the EMF equation. Okay, so there are two different methods are there to derive the EMF equation. There are two different methods are there. First method, that will be obtained directly from the principle of operation. Whatever the principle we have read, that we are supplying some alternating voltage, alternating current flows, and alternating flux is produced. And by using that definition, we can derive the EMF equation. So as per principle of operation, okay, the flux produced, let it be phi. As per principle of operation, we are giving some alternating voltage, alternating current flows, then alternating flux is produced, which is given by phi. And phi means if this is alternating one, we know that we are taking the help of an equation by using which we can represent any alternating quantity. That is, if you are taking an alternating equation which is given by x is equal to xm sine omega t, means in terms of a waveform we will get this one. Okay, this is your time axis and this one is your x. And this x can be a voltage, can be a current, any alternating quantity. So if you are taking an alternating flux, then phi will be equal to phi m sine omega t. So when you are giving alternating voltage, alternating current starts to flow, so that due to the alternating current, some alternating flux linked to the primary winding, which is given by phi is equal to phi m sine omega t. And as per the formula we know, as per the induced EMF, the EMF induced, let's we'll take a primary side. The EMF induced in primary coil or in primary winding. The EMF induced in primary winding, which is given by EP is equal to minus N1 into d phi 2 dt. This is the formula just now we have read. EP is equal to minus N1 into d phi 2 dt. And here we know phi is equal to phi m sine omega t. If in place of phi, if you replace by this one, and if you go to find out the time derivative, then you can say that this is equal to EP, which is equal to minus N1 d by dt of phi m sine omega t. Okay, now find out the derivative. You can say minus n1, how much? Phi m, phi is a constant, take it outside. Phi m into omega cos omega t. Okay, and omega means what? This is called as angular frequency. So in place of omega, we can write this one as minus n1. Okay, phi m. What is the omega value in terms of frequency? 2 pi into f into cos omega t. Okay, so now in the next step we can write okay, so up to this one we are getting minus n1 into phi m 2 pi f into cos omega t. So just make it properly arranged. So we can say next one is that EP is equal to how much you are getting? Minus 2 pi f n1 into phi m cos omega t. So now what we'll do, we will write in a proper manner so that this minus term can be removed. So now this will be equal to minus 2 pi f n1 phi m. In place of cos omega t, we can write this one in terms of sin 90 minus omega t. Okay, now this will be equal to minus 2 pi f n1 phi m. We are having sin 90 minus omega t. We can write the same one as if you are writing this one sin omega t minus 90, then here this we can remove the negative sign, because we know that sine of minus theta is equal to minus sine theta. Initially we have been sin 90 minus omega t. If you take a minus common, then you can write sin omega t minus 90. Sin minus of omega t minus 90 is equal to minus sin omega t minus 90. So here we are having a negative sign, here we are having a negative sign, both will multiply, we will get positive. So finally we are getting EP is equal to 2 pi f n1 phi m sin omega t minus 90. This is the voltage we are getting. But here for maximum voltage, for maximum EMF, this term sin omega t minus 90. Okay, so for maximum EMF, sin omega t minus 90 should be equal to 1, because what is the maximum value of this one? The maximum value of sin omega t minus 90 is equal to 1, not more than that. It will be maximum, at maximum 1. So if this part will be 1, then you can say, then we'll get EP is equal to 2 pi f n1 phi m. This is the voltage induced in the primary winding. So this is the maximum EMF. But you have to find out the RMS value of, then the RMS value of EMF induced in primary winding. RMS value of EMF induced in primary winding, which is given by EP is equal to, so if you know the maximum value, how to find out RMS value? What is the formula? So if you know the maximum value, to find out the RMS value, you have to divide maximum value to root 2. So now we know the maximum value is this one. To find out the RMS value, you have to divide the maximum by root 2. That is EP maximum divided by root 2. So you take this one as EP maximum and you take this one as EP RMS, so that you can find out the difference between these two. So if you divide EP max, which is given by this equation, divided by root 2, we'll get 4.44 f n1 into im. So finally you can say the EP RMS value or the EMF induced in the primary winding is given by 4.44 Fn1 into phi m. So this is the EMF induced in the primary winding. If you follow the same process, whatever the process we have followed, if you follow the same process, then also you can find out the EMF induced in the secondary winding. Just what you have to do, here in this case we have taken EP is equal to minus N1 into d phi by dt, and when you are going for a secondary winding voltage, as per I have told you that ES is equal to minus NS into d phi to dt. Okay, NS or N2. So ES is equal to minus NS into d phi by dt. d phi by dt will be same. Just in place of N1, you have to replace by N2. Same steps, same methods, same process. We can also find out that EP in the secondary winding, ES in the secondary winding is equal to 4.44 Fn1 into phi m. So we can say also we can find the EMF induced in secondary winding or in secondary winding, okay, which is given by ES RMS is equal to 4.44 F N2 into phi. Okay, just by you have to use the same process. Just in place of NP, you have to replace by NS or N2. Then also you can find out the same type of equation. So this is one method. So we can say this is this equation I have obtained from first method, that is directly from the principle of operation. Whatever the principle of operation we have read, depending upon that one, we can go for that. One more second alternate method is there. Okay, the alternate method. Okay, so in the alternate method, what we will do, we will take the flux. So this is the alternating flux, the waveform for alternating flux. Okay, flux along the y-axis, T along the x-axis. So this is the waveform for the alternating flux. So what we are doing, we are taking one time from 0 to, take this one as T by 4 and take the total time as T. T by 4, this is T by 2 and this is your 3T by 2 and finally again this one is T. So if divide the total time period, means the one complete cycle of a alternating flux into different regions. So if you are taking T by 4, initially flux was 0. When T is equal to 0, flux was equal to 0. And when taking T by 4, let's the flux is increased to phi m, the maximum flux. So we can say at T by 4, capital T, at T by 4, phi is equal to phi m, at T is equal to 0, phi is equal to 0. That means we can say initially flux was 0, but the flux takes some time to increase from 0 to phi m in T by 4 seconds. So what is the rate of change of flux? What is the rate of change of flux? As we know the formula, that is d phi to dt. d phi means change in flux, dt means change in time. So what was the flux changes? It was changed from 0 to phi m. dt, what is the time changes? 0 to T by 4. So what is the d phi? What is the change in flux? That is phi m minus 0. dt, what is the change in time? T by 4 to 0. T by 4 minus 0. So how much you will get? That is 4 phi m divided by T. So this is, we got rate of change of flux, and this rate of change of flux is called as average rate of change of flux. Average rate of change of flux is equal to 4 phi m divided by T. Then from this average value, we will find out the RMS value. To find out the RMS value, because whatever the voltage we have found out here, we have found out RMS value of the voltage. So here also we will find out the RMS value of the voltage. And to find out the RMS value of the voltage, you have to find out what is the RMS value of the change in flux. So to find out that one, we have read about form factor. In single phase AC circuit, we have read about a form factor, which is defined as the ratio of RMS value of an alternating quantity to average value of an alternating quantity. If RMS value is known to us, average value is known to us, and this is defined as 1.11, a constant value. Form factor is equal to RMS value to average value, that is equal to 1.11. And if in this case we know the average value, we are going to find out RMS value. So to find out the RMS value of flux, or take it the alternating flux, RMS value of alternating flux is equal to 1.11 into 4 phi m divided by T. So how much you will get? 4.44 phi m divided by T. Okay, and here T means what? T is called as a time period, and we know the relation between frequency and time period. Frequency is reciprocal of time period. So here we are getting 4.44 into phi m divided by T. That can also be written as 4.44 F into phi m. Okay, F into phi m. So this is the RMS value of the flux that is produced in the primary winding or in the secondary winding. If you know the RMS value of the flux, means that is d phi by dt is known. The RMS value of d phi by dt is known. So if you know the RMS value of d phi by dt, then you can find out the EMF just by using the same formula. That is to find out the RMS value, as we know that in the construction, in the operation, as I told you that the EMF induced in windings. Okay. EMF induced in any winding, either in primary or secondary winding, that doesn't matter. If you are taking primary winding, what is the formula? This is equal to N1 into d phi to dt. And here we know what is d phi to dt. This is 4.44 F into phi m. Just you have to multiply with N1 into 4.44 F N1 into phi. So finally get 4.44 F N1 into phi. So if you have taken this one as a N1, then we can say this is the EMF induced in the primary winding. If you are going for secondary winding, just you have to replace N1 by N2. So the next point you can say, similarly EMF induced in the secondary winding. Okay, that will be given by 4.44 F N2 into phi m. So mention here volt, here also volt. Okay, just by using the same formula, but only N1 replaced by N2, because there I told you that whenever we are transmitting the power, frequency will be same frequency. Whatever the input frequency will be there, the output will also have the same frequency. So here also we are having F value, here also we are having the F value. And phi m, the same flux linked, whatever the flux linked to the primary winding, same flux linked to the secondary winding. So here whatever the flux is present in the primary, same flux also present in the secondary. Just by depending upon the number of turns, either the transformer can be a step up transformer or it can be a step down transformer. So these are the some formulas, and these are the way how we are going to derive that EMF equations. Okay. So any doubt? Any doubt? Any doubt? No? No doubt?